Hi everyone, and welcome back to Fundamentals of Engineering with Mechanics of Materials Deflection. In this example, we review an interesting problem in statical indeterminate structures. In this example, we have like a combination of solid rods ABC, ABCD, as you can see here, ABCD, this blue rod, and two aluminum rods like CE and DF. And after applying a 10 kips at the point A, we want to calculate the forces in each rod and also the deflection of them. So the specification, the material, the diameter of each of them is provided. So the problem statement is the aluminum rod, one of them CE is provided to be half an inch in diameter, and the other aluminum rod is three quarter of an inches. When a force of 10 kips apply at point A, we want to know what is the forces in each rod and also the corresponding deflection of point A, and also the deflection in CE and DF. To do so, we first need to draw the free body diagram of rod a rigid bar of a B C D, as you can see here. When we have the free body diagram, we need to have the forces on that. So it's like at point A, 10 kips force applies. At B, we have like a pin. So we have Bx, By, and at C and D, two forces of FCE and FDF related to those rods applies to the free body diagram of rigid bar ABCD. And if we jot down the moment equation about point B goes 0, we can have like force at A, which is 10 kips counterclockwise, which is a positive, times the distance arm is 18 inches, minus FC, which is a clockwise, which is a negative one based off our arbitrary direction. That's FCE times 12 inches. This is the distance, minus another clockwise moment, that's FDF times the arm from B, which is 20 inches. That goes 0, and it just gives us the first relation based off statics, and it just gives us 12 FCE plus 20 FDF is 180. We call this equation number 1. This problem is pretty interesting because it uses statics, geometry from physics, and also the mechanics of materials in terms of deflection calculation. We are in the first part, which is the statics equation. Based off the forces, moments, it just gives us equation number 1. Based off physics or geometry, we can easily see the deflections of point A to A prime, C to C prime, and D to D prime after applying 10 kips at A. At A, there is a downward pull, and it just let there is a rotation about point B, and it just lets point C goes up to C prime, D goes up to D prime, respectively delta D, delta C, and delta A creates there. And we have the relation. If based off the geometry, we just use the triangle and use delta C over 12. Delta C over 12 is equal to delta D over 20 inches. It just gives us a relation between delta C and delta D, and also delta A over 18, delta A over the distance is equal to delta D over 20, and it just gives us the second equation. We've got our first equation based off statics. The second and third equation comes from geometry of the deflection, which are these two equations. Delta C is equal to 60% delta D, and delta A is 90% delta D. Equation 2, equation 3. Let's move on to the formation part. Each of these two rods are extended. It's a pulling force at point C and D based off the geometry which we observe, and there is an increase in the length that's called delta C and delta D in each of those rods. So based off mechanics of material, delta is nothing but FL over EA. So delta at C is equal to FCE times length of CE over area of CE modulus of elasticity of the aluminum, which is provided in problem statement. Likewise, do the same for delta D, FL over AE. E is the same because the material is both aluminum. And then if we just jot down our equation 2 and 3 again based off our geometry, we get this relation, and delta C is equal to FL over EA for C, FL equal over EA for D, and then substituting for delta C and delta T in equation 2, it just gives us delta C is equal to 6.6 delta D, and it just gives us this relation FCE times LC over ACE times modulus of elasticity is 60 point of FL over AE for rho dF. As soon as we have this relation based of mechanics of material, we can calculate it for FCE. And if we just jot down the FCE, rearrange the equation, reach to this one, and replace the numeric value, it just gives us FCE is equal to this numeric value times FDF. And if you do the math, it just gives us FC is equal to 0.333 times FDF. Force in each rod is then easily calculated based off our first equation from statics. FCE is calculated, replace in the very first equation. If we remember, we got this equation based off the statics, based off a creation of moment about point B. It just gives us 12 FCE plus 20 FDF is equal to 180, and that's our equation 1. Replace FCE in this equation, and it just gives us what FDF is easily calculated in this equation. One equation, one unknown. And then you can also jump to the first equation and also calculate FCE based off FDF. That's this numeric value times FDF. Replace it and you get both of those forces in each rods. Then the deflection calculation. Let's move to point D in rod FD or DF. FDF is already calculated to be 7.5 kips. And then delta D is FL over EA. Replace the numeric value and it just gives us delta sub D is equal to 48 times 10 to negative 3 in terms of inches. Likewise, the deflection of point A is also calculated based off equation 3. We already know what delta D is, and delta A is 90% of delta D based off our third equation in previous part. And if you just replace it in the equation, it just gives us delta A is equal to 42.2 times 10 to negative 3 inches. An interesting review for this problem is that we do know as the rigid bar rotates about point, as the rigid bar ABCD rotates about point B, the deflection at C, and deflection at D are proportional, linearly proportional from the pivot at point D. So, but the forces are not, and there is a question, why is that? Why the this displacement are proportional, but the forces are not? The answer to this question is pretty interesting because it just says for an aesthetically indeterminate structure, the forces doesn't depend only on deflections, but also there depends on the equilibrium of the rigid bar. Thank you. We'll solve more problems related to chapter 4.